Hello. So in this video, we are going to be covering the graphing part for inequalities. And so we've sort of talked about like graphing solution sets and such, which we're going to also go through in detail here. So this is the case where we have basically one variable, but turns out that it gets a little more complicated, maybe unsurprisingly, when we have more than one variable. So we're going to sort of be talking about that part too. Okay. So first up, graphing inequalities. So if we have just a single variable, right, like we have here, x greater than or equal to -3, and just to be, again, sort of painfully clear here, it's greater than because it's on the sort of bigger side, and the bar underneath is the or equals to part, right? So here we want to sort of represent the idea that x can be any value that's sort of at least as big as -3, right? Sort of technically incorrect to say bigger than -3, like in a very technical sense, because it also includes -3, right? So usually we say at least as big as, or at most if it's going the other way. So for example, we want to include the answer -3, right? Because that's at least as big as -3. But we could also include -2, 0, pi, right? They don't have to be nice numbers. We could even throw in 3,287.15, right? We want all of these answers. In fact, we want sort of infinitely many. So here, -3, we often call this a lower bound, and that's because it's sort of the lowest value we accept, and we'll take anything bigger than that, right? So we represent this in interval notation with this sort of classic bracket, right? Because we're including -3, and we go up to positive infinity, which again just really means that we'll take anything sort of in that direction, so anything bigger than -3. All right, so sort of follow-up question, how do we actually graph this? What do we mean when we say graphing inequalities, right? So on the one hand, we want to represent that we have this sort of important point to keep in mind, right? The -3 that we need it to be at least as big as. So we fill in that circle. And in fact, we use a filled-in circle because we want to include this thing as opposed to an open circle, which we'll see in a little bit, where we want sort of everything up to but not quite that value. Moreover, as we mentioned, right, like -2 works, 0 works, pi, which would be like around here, that stuff works. So really, like all that stuff to the right works. And in fact, not just right here we have, up through like a little past 6 or whatever, but that's not all of it, right? In fact, we can keep going for anything, 3,287.15 or whatever it was, right? So that thing is represented by the arrow, right? So again, all three of these parts are important. We have the filled in circle at -3 telling us that -3 is included, the line telling us that all this stuff that we sort of have written down is included, and the arrow tells us that in fact it just keeps going. It doesn't stop where the actual bar stops, okay? So this is how you would graph x greater than or equal to -3. As another example, if we want to sort of go the other direction, right, this would be at most 5, because again, we count 5. So we do this the same way. We'd fill in the circle at 5. We sort of color in the bar as far as we've sort of written down, right? And then once we get all the way to the edge of our number line, we include that arrow bit to tell us it actually keeps going forever, okay? So this would be the graph for x less than or equal to 5, or x is at most 5. So a common sort of situation to run into is that we want sort of everything up to a point, but we don't want that point, right? So this is very common for like domains, for example, right? Where you might have like x minus 3 in the denominator, and you don't want to divide by 0, so you can have sort of everything up to 3, but not 3 itself. So that's usually where we see these strict things. So we would say 3 is strictly larger than x, or x is less than 3. And again, we would do this by the sort of same process, but now we don't want to include 3, so we use an open circle, right? So we have the open circle as opposed to a solid green dot to say that we want everything up to 3 but not including, and then our bar, and then again our arrow that shows that we keep going forever, okay? Last but not least, it's very common to have sort of range that we're looking at. So we would say something like x is greater than -3 and at most 5. X is between -3 and 5 or 5, right? Because if I just say between, usually we want strictly between. But any of these things would sort of work. Again, this is why English language not necessarily so great at being precise, so that's why we have these symbols to be very clear what we mean. But otherwise, the same sort of process works. We want to include 5, so we throw in that closed dot. We don't want -3, so we make that an open dot. And we want everything in between, so we color in between. Notice here we're not using an arrow because we don't want to go forever in one direction, right? We want to have sort of strictly between these two things colored in, and then we want 5 as well covered in, okay? All right. So that's one-dimensional inequalities. What about two-dimensional? So what we mean by that is what happens if we have a y and an x instead of just x, right? Well, now that we have y and x, we're going to graph this very much like we would sort of a normal equality or a normal equation, right? So sort of the thing to think about is instead of thinking of this as y less than x, we start out by thinking of it as y equals x. And then we just sort of graph that curve, graph that function. So if we graph this, right, we have our line on the xy plane going straight through the origin, 45-degree angle, sort of very classic sort of parent function here, right? Now, there's a technical way that one should, that technically is the way that we color in or we decide where the sort of solution set is. And I'm trying to be very clear here that there's sort of a very technical way to do it, which I'm going to show you in a second, but there's also sort of a colloquial way or a much sort of easier conceptual and mechanical way to do it usually. So technically what's going to happen is that we look at one particular x value and we look at all y values along that x value. So here I'm looking at all of these x equals 1 values, right? So along this line, the x is 1 everywhere, but like down here, y is -1, down here, y is -2, -3, up here we have like y equals 4. In particular, I'm going to label this y equals 1 spot, this 1, 1, because that's where it hits the curve, right? Or I say curve, but hits that y equals x line, right? So this is where it sort of intersects, is where you have x is 1 and y is 1, which makes sense because, right, we have y equals x is the curve where they're equal. So this thing has a fancy name. We're not going to use it again in this class. You don't need to know this, but it is something that comes up later on in calculus. Things called, typically referred to as a level curve or a slice of the function. And the idea is that what I'm going to do is I'm going to look at this particular x value, right, x equals 1, and then I'm going to look at it as a number line. So think about taking this thing, this up and down curve, and sort of laying it down so that to this right part is this up part here, and this left part is really this down part here. And that way I can look at it and say, okay, these are all the y values, right, because I'm going up and down. And I want y to be the stuff that is to the left of x. I want less than x. So that tells me that I really want to the left of x. So I really want this thing to be my solution set along this line. So what that's telling me is if I sort of rotate it back in place, that's actually the part that sort of is the solution set for that particular x value. And the real takeaway that I'm looking for here is that this tells me that if I'm looking at the curve, like anywhere along that curve, for any part where it sort of intersects, I could do the same level curve idea and then look at it and see that it's actually going to be colored below, which means my solution set is really everything underneath the curve, okay? Now, as I mentioned, this is the very technical sort of situation where this thing is occurring. For something as relatively straightforward as a two-dimensional sort of graph here, like the y and the x piece, this is sort of a very difficult way of going about this process. So generally speaking, we do it a different way, which I'm going to show you in a moment. So if you didn't 100% follow what I was talking about with the level curve and seeing how it's sort of oriented, don't worry about it too much. This is a thing that sort of is much more useful as you get higher dimensions. So if you go into, say, multivariable calculus and you're doing three-dimensional plots, sort of difficult to understand what a three-dimensional plot looks like, so a lot of times we'll take these slices or these level curves and look at two-dimensional pieces in various places. So this is, for example, how like topographical maps tend to work, is they have ways of denoting different heights, and those are really sort of slices through heights and show you where it would intersect the terrain in order to give you an idea. All right. So that aside, as I mentioned, there is sort of an easier way. So another way we could do this is we could think about this as saying, okay, we have this line, right? We have this y equals x line, and we know sort of one side of it or the other, sort of at least one side of this is going to be the solution set. In very rare cases, it's possible that both sides work, in which case there's something weird going on with the underlying inequality, but it's important to remember that both sides could work for reasons I'm going to show you in a second. But the point is sort of if some point on one side of that line works, then all the points on that side of the line work. And so we can use that, sort of abuse that idea by testing points. So I'm going to pick 2 points, basically whatever points I feel like. It's usually a good idea to pick points that are sort of easy to compute with. But the sort of important thing is I want to pick points on either side. So if I think of this line as cutting all of this graph sort of in half, but in this diagonal sense, I want a point from either side, right? I don't want 2 points on the same side. That wouldn't help me. Then I want to plug in those values because, again, think about this. This is an x comma y value, right? X comma y value. I want to plug these values into my inequality and determine whether or not what they're saying is true. So if I look at this first one, for example, x is -1, y is 1. So that would give me the inequality that 1 is less than -1. That's not true, right? So what that tells me is that if that point isn't true, that point doesn't satisfy my solution, it's not part of the solution set, which tells me everything on the same side of the line is not part of the solution. I don't want to color anything up here, okay? Now, it's easy to think like, well, if it's not up there, it must be the other one. That's not always true. So it's sort of important that you actually test every point and don't sort of assume that, like, if you find one that works, the other one must not, or if one doesn't work, the other one must. That's not always the case. So I'm going to do the same thing I did a second ago, but I'm going to plug in now the other point, right? So where x is 1 and y is -1. If I plug that in my inequality, I get -1 is less than 1, and that is indeed true, right? So that tells me that every point on that side of the curve, every point over here, is going to be in the solution set, which tells me I want to shade everything underneath. Okay? So this is sort of a much easier way of going about this than the level curve instance when it comes to two-dimensional stuff. So the level curve is sort of useful to see for future math courses if you're going on into calculus and things. But for the sake of this class, almost certainly you're going to be doing some variation of this when it comes to inequalities. Okay? All right, so let's look at a more sort of complicated version. So we want to find a solution set, but now we want a solution set that is sort of bounded by 2 different functions, and these functions are kind of unpleasant. I mean, they're not terrible. They're polynomials. We could sort of figure out how to graph them. But when we look at their graphs, I have something weird going on. It's not as simple as like having above the line and below the line or something like this, right? So there's 3 different ways that we could sort of try to figure out the solution set. The first way, we could try that theoretical approach, the level curves and taking slices and stuff. But it was already sort of difficult to keep track of stuff even with the very straightforward line case. So you're not really going to want to do that. Option 2, well, we could try sort of mapping out each region, like try finding every single region and putting a point there and testing that point in both inequalities. And then that would tell us sort of which regions work, which regions don't. So that's sort of equivalent to what we did before, where the line cut the thing in half, so we only had 2 points, right? Because we have 2 different regions. But if we have more regions, we need more points to check them. Okay, so that's another option. Turns out that one's not going to be great, and we'll see why. But it comes down to the fact that there's really deceptively more regions than you might expect in here. Option 3 is we could really just look at each of the functions, right? Because we have 2 functions here. We could look at what the solution set is for each one individually and then determine where they overlap. And where they overlap, that's where it's going to be sort of a solution set for both at the same time. That's what we're after, okay? So option 1, not really a great plan. It's sort of already annoying in the best sort of scenario, and this is far from the best scenario, right? Option 2, well, we would try to break this up and identify every possible region. But if I did that, turns out I'm going to have all of these regions to look at, right? So I have the one that's sort of all the way to the left. I have the one that's below both of them, above both of them. I have the one that's in the middle. I have one that's between them in this way, one that's between them in this way. So I have all kinds of these regions to sort of check and go through. Now, it turns out there's some weird stuff you could do to make some arguments about, like, maybe some of these are redundant. You don't have to check them. But again, this is sort of going down a rabbit hole that's a lot of work to go through. So a better way is that option 3. So we're going to sort of reduce or look at the case where we're going to do one at a time, sort of independently, and then look where those regions overlap. And I'm going to do this the same way we talked about that sort of option 2 for the line, meaning that I'm going to look at this as this curve breaks up my region into 2 places. I have sort of above and I have some sort of below, right? And I'm just going to pick 2 points that are sort of easy to use to calculate. Again, there's no reason to make this hard on myself. So the 2 I'm going to sort of just choose, I'm going to look at the origin, 0, 0, which is the one that's below the curve. And then I'm going to look at this one, 2, 0, which is the region above, all right? And then I'm going to plug these into the inequality that this function represents. This function here, this red one, is my cube, right, my f of x. So I'm going to plug in 0, which is the y value. That's what f of x equals. And I can plug in 0, the x value, into this side, compute, and see what I get, right? So if I do that, I get on the left, the f of x is 0, because that's the y value. I plug in 0 for x, and I calculate it through, and I get 4. So this gives me an inequality that 4 greater than 0. That's good, right? That works. Again, we don't want to fall into the trap of just assuming that means that the other one doesn't. We do want to check the other one. So the other one, same idea. The y value is 0, so I'm going to have 0 on the left, and then I'm going to plug in 2 for x and calculate. And if I do that, I end up with 0 less than, plug this in and calculate, -6. 0 is not less than -6, so that tells me that this one is not part of the solution set, okay? So all of this together then, what I find is that everything below that curve is the solution set. So I can sort of shade in the underneath part. If you're doing this on your own paper, it can be helpful to sort of do like scratch marks or whatever in one direction and then do a different direction for the other function when they're like laying on top of each other. We'll see what I mean in a little bit. So now I'm going to look at the other function, right? The other function is that the parabola, right? The g of x, which is just this quadratic here. But again, same idea. I'm going to pick 2 points, 0, 0, and 3, 0, let's say. Again, I want to make sure I grab one that's sort of above versus below. And then I'm going to plug in those values. So the y value, right, is 0. So I'm going to have 0 less than. And then I plug in 0 for x and calculate. I get something like -2. That's not the right, value, right? So this is not true. For the other one, same idea. I'm going to plug in 0 for the g of x because my y that I chose was 0. I'm going to plug 3 in for the x, and if I calculate, I get 4. That gets me 0 less than 4. That is true. So since that one's true, the other one is not true. That tells me that my solution set really is everything underneath, okay? So I found the solution set for f of x. I found the solution set for g of x. Where those things overlap, that's where my solution set in general is. So when I put these on top of each other, right, I have all of this area down here, but not between, because between is only a solution set for f, but not g. Then I have all of this section over here, over down here. This part is not, because that's only a solution for g, not f. Up here, only f, not g. So again, not that part. So I can sort of reduce down to where they both work. And again, just as a sort of quick reference going back, this is if you're doing this by hand, especially if you don't have different colors, because most people don't have different colors, a lot of people will do this by doing sort of scratch marks, say top right to bottom left for all of the G stuff, and then they go from top left to bottom right for all the F stuff, or whichever way you want to do it. And then you can sort of see where they crisscross, right? Where you have both of those and they're making a crisscross pattern. That's where they overlap, and that's your solution set. All right, so what do we do? Well, we talked about graphing inequalities, the solution sets of inequalities. And we did a bunch of stuff with single variable where we had to worry about the open, closed dot and the arrow or not arrow situations. And then we moved into two variable, which gets more complicated, but it's sort of, at least in spirit, very much the same idea, where we're sort of looking at a graph, only now it's an actual like XY plot, so it's a little more interesting than a one-dimensional plot. But nonetheless, we're looking at a graph and then we're sort of shading one section of it to represent that sort of solution set. And if we have more than one function that we need solution set for, we're really looking at where they overlap. And this was true in the single variable case as well. So when we're doing that, it's sort of easiest to do one piece at a time and then look at where they overlap and then identify that as the solution set. Okay, so that is that.